Okay, welcome to a live session. This will be the last for the Coursera cohort, so I'll say a sad farewell to all of my students with Coursera. Udemy will continue, and we hope to move to an open enrollment Coursera class in the summer. The floor is open for questions on any topic.
Right, the first question is from Carol, and she asks, two scientists have come up with the idea that Jupiter migrated towards the sun and back out again. What are your thoughts on this very new and interesting possibility?
So planet migration is a new concept that came about when we first discovered exoplanets and were surprised that so many hot Jupiters were among the first exoplanets. Now, there's a strong selection effect there because it is much easier to find massive planets on tight orbits because the signature is both larger and the orbital time is shorter. So with exoplanets, it was easy to find the hot Jupiters, and it's taken a while to realize that most exoplanets are not hot Jupiters. But roughly 10 or 15% of the exoplanets found so far are hot Jupiters. Clearly, we have no giant planets in our solar system that close in. Our solar system segregates neatly into the rocky terrestrials in the inner part, and then the gas giants, which include small rocky cores, but they've accreted large gaseous envelopes in the outer part. So this idea came about that planets must migrate. The reason being that if you try and form a gas giant very close to its star, there's simply not enough material. It's physically impossible in a normal accretion scenario to form a giant planet close into its star. So the inference was that planets must migrate, and eventually theorists understood mechanisms by which giant planets could migrate from further out. So exoplanets gave us the idea of planet migration. But that, of course, is in one direction. It's giant planets forming further out and migrating in. As an aside, what happens to a gas giant planet when it migrates, and this tends to happen very early in the history of a solar system, probably the first 100 million years, is that it can, depending on its orbital parameters, it can tidally lock into a tight orbit of the star, or it can just continue to spiral in and become part of the star. And in the early history of solar systems, we think a number of the proto-gas giants actually just feed the size of their parent star, and maybe occasionally they pop on an orbit to become a hot Jupiter. So planets can move around. That was the first and the most important realization out of exoplanet studies in the late 1990s and early 2000s. A separate idea that has been in play for a couple of decades is that planets can undergo resonant changes in their orbits. Basically, when the orbits of any two giant planets, this works best, of course, for massive planets, is a ratio of integers. So the ratio of the periods being 3 to 2 or 4 to 5 or 7 to 8, any pair of integers. When the periods of two planets fall in that way, then they receive periodic kicks, which is a resonance situation, and that can disrupt what would otherwise be stable orbits. So the resonance phenomena has also been understood, and we think in our early history of our solar system, resonance played a role, and in fact rearranged the positions of several of the outer planets. Resonance can work, not generally does work, to move planets outward rather than inward, and in fact sometimes can eject planets entirely from the system. So we have a mechanism of migration which can lead to a giant planet going in close towards its star and maybe being swallowed by the star. And then we have resonance phenomena, which depending on the orbital parameters can upset the orbits of planets, rearrange them, or even eject them entirely from the system. So basically you see that almost everything is possible. This recent research is suggesting that Jupiter has not always been at the place it is, that our solar system in fact formed with more than the original complement of 4 terrestrial rocky planets, and that movements of Jupiter in and then out scattered like 10 pins some of these extra planets, leaving us with the 4 terrestrial planets we now have and know about, and having Jupiter finally end up in its current position. So it's an interesting idea, and it incorporates, this thinking from the last few decades. Proving these kind of ideas is extremely difficult for one simple reason. Even though gravity is a fairly simple law of motion describing any two massive objects, in a system like a solar system with multiple objects, the number of interactions is obviously significant. It goes up as the square of the number of objects. So if you have 5 massive planets and 1 star, you've got 30 different gravitational interactions. Following those interactions for what amounts to millions of different orbits, because the planets are orbiting every few years, and you're following them for tens or hundreds of millions or even billions of years, becomes an approximation. Even with a powerful computer, you can't do it with perfect precision. So all of these speculative scenarios of planet rearrangement, ejection, and so on, including the one that Carol was asking about, are somewhat uncertain because we cannot, with true fidelity in a supercomputer, simulate what did happen. In other words, we can't run the clock backwards from the current situation towards the initial conditions, especially towards these early situations, in part because the phenomena are chaotic, which implies that they're nonlinear, which implies that very small changes in the initial conditions lead to very different outcomes. And so we sit now with the outcome that we can see after 4.5 billion years and have great difficulty inferring what happened early on.
All right, the next question is from Fazad. We know that according to general relativity, mass bends space-time. So is it possible for the mass of something to be so great that it actually rips the fabric of space?
Certainly. The theory of general relativity is essentially a geometric theory of gravity. That was Einstein's great insight. Newtonian gravity hypothesizes a force operating between masses, but then holds space and time to be linear and absolute and independent of each other. In general relativity, space and time are coupled through a very particular set of equations which incorporate the energy density of mass in a particular region, and that relates to the curvature of space-time, which is now a hyphenated entity, so it's linked. So space-time curvature in a modest sense, such as the distortion of space-time caused by the Earth or the Sun, is calculatable by an approximation. It's not derived in Newtonian theory, because Newtonian theory makes no such prediction. But most of these curvatures are fairly modest. The curvature that's extreme is, of course, from collapsed objects such as neutron stars, pulsars, and then black holes. And in the formalism of general relativity, a black hole does represent a region of space-time that's essentially sealed off or so heavily distorted that it's removed from the continuum of space-time at more remote regions. So you can think of it as a piece of space-time, if you like, that's ripped out of our space-time, where the boundary for that invisible region is the event horizon. So remember, that's a metaphor. These are descriptions that really have to be done in terms of the mathematics of general relativity, but it's a correct metaphor to think of these as pieces of space-time ripped off from our present-day universe. An interesting question in cosmology is whether, outside of collapsed stars like black holes or even supermassive black holes, it's possible for space-times to be segregated or ripped apart, if you like, or separated on much larger scales, like cosmic scales. And that's something that might lead to a multiverse scenario or parallel universes. And that possibility is certainly held open by current cosmology, but we don't have any observational indication that that's going on, because the space-time we see on global scale is actually quite close to flat, so it's fairly uninteresting and almost Newtonian space-time.
Okay, the next question is from Kirsten. Gravitational lensing fascinates me. My question is, when utilizing gravitational lensing to view a very distant object, is there an effect on redshift? If so, what is it?
Yes, so gravitational lensing is a manifestation of what the last question was asking about, the distortion of space-time caused by mass energy. And that distortion of space-time does lead to an energy effect. So you can think of space-time, if you want the two-dimensional analogy, the rubber sheet and distortions in the rubber sheet, bending it downward when there's a mass. You can think of the extra energy required to rise out of a gravitational field. Now that extra energy applies to light as well as mass, because they're related by E = mc squared. And so photons traveling in gravitational fields, intense gravitational fields, do have to struggle against the gravitational field. So it's just as much a prediction of general relativity as the distortion of space-time itself, that light traveling in distorted space-time regions will suffer energy loss when it's escaping from a stronger gravity region, and that energy loss manifests as a redshift, a gravitational redshift. So gravitational redshift was a prediction out of general relativity way back in the 1920s. It was worked out in detail. But gravitational redshift is very hard to observe because in most cosmic situations, this effect, because gravity tends to be weak in most regions, this effect is far too small to observe. It's parts in a billion or parts in a trillion. A black hole, of course, indicates a region where space-time is separated, and so conceptually you can think of the gravitational redshift as being infinite. The photon is degraded in energy so much that its wavelength becomes infinite, its energy becomes zero, and operationally it does not leave the black hole. That's the event horizon, the boundary of information, matter, and radiation. So gravitational, as much we think black holes exist in the universe, and we found a number of them, then they are subject to this gravitational redshift. So gravitational redshift does seem to be real, and it has been measured both indirectly in many ways and directly in a few special situations, such as binary pulsars. So gravitational redshift is real. It's at its most extreme in the situation of a black hole, but it also occurs in more mundane settings, such as in the lensing we see with large clusters. There will be a very slight gravitational redshift applied to light from more distant objects as they pass through the gravitational potential of an intervening cluster and lead to those beautiful arcs and rings that you see in Hubble Space Telescope images.
All right, the next question is from Patricia. Do you think we can justify the cost of searching for life if it turns out we find nothing but microbes or insects?
That's a good question, and of course, part of answering the question involves the cost. What is the cost of the search for life in the universe? I think astrobiology as an entire subject, an outward-looking subject, there's part of astrobiology involves studying the Earth, of course, for the origins of life and extremophiles and so on. But if we take the outward-looking part of astrobiology, it's actually quite a modest part of the astrophysics portfolio. To be specific, NASA has a space science and astronomy budget that's roughly $3.5 to $4 billion out of its $18 billion budget. And I think in most years, only 150, maybe $100 million is spent on astrobiology. So NASA is really spending quite a small fraction of its overall budget on astrobiology. National Science Foundation is spending almost nothing because it has no astrobiology program, unfortunately. So astrobiology, the search for life in the universe by astronomers, is actually a very modest endeavor. And in that sense, we're not really spending a lot of money on it. So I don't think it's an unwise cost at the level we're doing it. Most of that money, of course, goes into finding exoplanets and characterizing them. And the most expensive experiments that are coming up will be the ones that try and find life indirectly by its alteration of a planetary atmosphere of an Earth-like planet elsewhere. So we'll be looking for oxygen, ozone, methane, other biomarkers in the terrestrial atmosphere tens or hundreds of light years away to indicate that microbes exist on that planet. Now that kind of work is expensive because it actually requires new generations of telescopes, the James Webb Space Telescope, for example, and the very large telescopes like the Giant Magellan Telescope we're building here in Arizona, so 20-meter class telescopes. Those telescopes and those missions cost billion or more dollars, but those missions, of course, do a whole range of science, so they're not being built just for this one experiment. This is just one of the most exciting uses of those facilities. So even in that sense, it's not an extremely expensive undertaking. But the instruments to do this kind of work are expensive. They cost tens of millions of dollars to measure redshifts accurately enough to find really low-mass exoplanets like Earth's, and to build huge and stable spectrographs sufficient to sniff the atmospheres of those planets and detect life. So that's probably where most of the cost goes, into these fantastic and powerful and sensitive instruments. This work is going to go ahead because the scientific question is so compelling. So back to the question, is it worth it just to find microbes or maybe insects? I'd make a big distinction between those two categories too. We can only really detect life indirectly in terms of atmospheric alteration by microbes. The oxygen we breathe was put into the atmosphere of the Earth by microbes that started living 2.5 to 3 billion years ago, and it took almost 1 billion years for that oxygen to be put in place by microbes. So that will be the first and most plausible detection of life elsewhere, inference of microbes from atmospheric alteration on a global scale. Finding bugs or insects or plants is much harder, actually, even though they have their own imprint on the atmosphere, either in terms of energy or their metabolism or breathing or photosynthesis, for example. But those experiments are much harder to do. So it is just a very difficult experiment to find life other than a global imprint of microbial life. And people are still scratching their heads trying to figure out how best to do that experiment. SETI, of course, jumps across the whole uncertainty of the evolution of microbial life towards intelligence and technology, and just assumes that in some cases that happened, and then goes out and looks for technological signatures of civilizations. But that's a completely different experiment, and also quite a modest-priced experiment.
All right, Stefan, who is on live, would like to know, do you think we will be able to harness nuclear fusion in the near future, and as such provide a better energy source?
So fusion, of course, would change the stakes for space travel substantially. One of the reasons space travel has been in the doldrums is because we still rely on chemical technology, chemical rockets. This shouldn't be a surprise. We still, for the most part, drive cars that use fossil fuels and chemical energy. We still heat our houses with fossil fuels and chemical energy. So our civilization essentially runs on chemical energy. I think in countries like France and a few others, nuclear power, which is, of course, is fission energy, maybe gets up to about a quarter to 40% of the power. But really, we're a chemical civilization. And rockets are just very high-powered chemical fuel. Kerosene and its variants are the most efficient and volatile forms of chemical fuel. And that's how rockets work for the most part. So to do much better, we would have to go to not fission, but a fusion source, as the question implies. Well, as we know, fusion is an extraordinarily difficult reaction to harness. Fusion as a power source for our civilization has been held up as a way forward for half a century because, of course, it takes hydrogen and the byproducts are water. There's no radioactive byproduct. It's the cleanest form of energy you can imagine, and it's extremely efficient. It's just extremely hard to arrange, too, because you have to create temperatures, just as in the center of the sun, of maybe 10 million Kelvin, and sustain that. That's a temperature that would vaporize any container, so you use a magnetic bottle, and that's proved extremely hard to do. So for space travel, you have essentially the same situation. We've got a technique, fusion, which we know how to do in an uncontrolled way in a bomb. Fine, we figured out how to do that half a century ago. But in a controlled way, we only can manage it for tiny fractions of a second, and not in a way that generates sustainable energy. So really, until we are starting to see fusion reactors working in a mature sense on the Earth, it's implausible to imagine that miniaturized versions of them could work in space. I would say the only concept that probably could be implemented in the next 10 years using fission, and actually a bomb technology, it came from the Project Daedalus from the Brits back in the 1960s and 70s, and it's been updated since then. It's the idea of having many, many miniaturized nuclear explosions and detonating them behind a spacecraft, and then having a large reaction plate attached to the spacecraft, and essentially using the force from a whole series of thousands or hundreds at least of small nuclear explosions, fission bombs basically, but not fusion bombs, to propel the spacecraft. So it's a pretty clunky and inefficient way of moving a spacecraft, but it's still better than chemical energy. So that concept's on the books, and nobody's yet figured out how to make hundreds of coordinated miniature bombs propel a spacecraft. So it's purely a concept at this point. So my guess, unfortunately, is that we are decades away, maybe half a century away, from making fusion a plausible power source for moving around in space.
Right, the next question is, let's see, from Kirsty. Given that elliptical galaxies are much older than spiral galaxies and much more numerous, the formation of spiral galaxies must be a more recent phenomenon in the history of the universe, yes? What was different about the conditions of the universe then? and essentially what makes a spiral galaxy instead of an elliptical one.
So the biggest distinctions between spiral galaxies and elliptical galaxies, and of course, just to keep everything in view, there's a third category of irregular galaxies that do tend to have younger stars and a lot of gas, but don't have the grand design spiral or the smooth and uniform disk component of a spiral galaxy. But let's simplify to spirals and ellipticals. So the biggest distinctions in terms of their dynamics are that elliptical galaxies are a large number. Ellipticals tend to be more massive and physically larger on average than spirals. These are old stars moving entirely on elliptical orbits, and the elliptical appearance of the galaxy is just a snapshot in time of the hundreds of millions or billions of star orbits that are each elliptical about the center of mass. So they're more or less symmetric. Elliptical galaxies are elongated in 3 dimensions, but that elongation is usually modest, rarely more than a factor of 2. So they can be squashed a factor of 2, but they can be almost completely round. Spiral galaxies, of course, are spiral disks. They do have a spherical or nearly spherical component, their halo, which has a significant amount of the mass. So the best way to think of a spiral galaxy is a galaxy that had a lot more angular momentum than an elliptical galaxy did. And that angular momentum led it to preferentially collapse along the rotation axis and form a disk. And mass falling into that disk fueled star formation over a long period of time. And that process continues in the Milky Way itself. So we think spiral galaxies and elliptical galaxies differ based on their initial conditions, on the density of the region of space where they originally formed, and on the amount of angular momentum that large volume had in the early universe. The universe is not completely still, it's sort of chaotic and turbulent. So turbulent processes will generate small amounts of angular momentum in particular volumes, even though the total amount of angular momentum must add up to 0 because the entire universe, we don't think, is rotating. So you can, through turbulence, have angular momentum generated. And the more stronger amounts of angular momentum are the regions that would form a spiral galaxy. Now, but that leaves a lot of questions, and I'll truncate my answer because this is a whole big topic in astronomy. Many of my colleagues, hundreds of my colleagues, spend their lives working on research on galaxies and how they evolve and form and interact. So it's a huge subject. But we do know that spiral galaxies tend to be younger. They probably formed later. They evolve by eating gas and other smaller galaxies from the surrounding medium. And so we see that happening. Our Milky Way is caught in the act, from recent observations, some even in the last year or so, of devouring dwarf galaxy companions. And we can see several of those smaller, maybe 10 or 100 times less massive. Elliptical galaxies also have companions. They tend to be found in higher density regions, but the dynamics or the typical velocities of the galaxies in those regions are quite large. So mergers are relatively rare. So they also, this is a large-scale difference between spirals and ellipticals. The spirals tend to be found in lower density regions of the universe, large-scale, lower density, like the local group, our region of the universe, which has 2 significant spirals and a few dozen dwarf galaxies, is a generally low-density region of the universe, whereas the Virgo and Coma clusters, the 2 largest concentrations of galaxies which are rich in elliptical galaxies, are much higher density regions of the universe. A final point I'll make about this is that while Hubble's tuning fork idea as an evolutionary scheme turned out not to be right, we have good evidence that spiral galaxies, when they interact and merge, and sequentially over time, maybe even with smaller companions, can eventually turn into ellipticals. If 2 spiral galaxies crash together and the gas heats up, form stars, the stars relax, some stars will be ejected. When those stars age, their orbits will circularize in 3 dimensions, forming a more elliptical type distribution. And seen after 1 billion or 2 years, those stars will have reddened, the gas will have dissipated or been blown away by the star formation itself, and you'll have something that looks like an elliptical galaxy. So we do think on occasion that younger elliptical galaxies, the ones that didn't form very early in the universe, have actually formed from the mergers of spirals.
Okay, the next question is, with the new finding of nitrogen on Mars, why is this so important?
Well, the Mars research is pursuing a number of lines to try and identify how habitable Mars was. It seems that Mars is not habitable now, on the surface at least, because the atmosphere is thin, the cosmic ray and UV radiation is intense, so the top centimeter or so of the Martian soil, or regolith, is essentially sterilized. Also, there's not a lot of organic, carbon-rich material visible on the surface. But the study of the rocks using these spectrometers attached to the rovers, especially the Curiosity rover, which is very sophisticated instrumentation, has started to identify the ingredients of life. Now, all those ingredients, of course, include carbon-rich material, but they also need to include nitrogen-rich material. In the acronym CNOCH, the nitrogen is one of the biogenic elements. So to form biological material, nitrogen's not as important as carbon, but it's essential for the backbone of the phosphate that might store energy in some biological mechanism, and in a number of other ways. Also, it serves as a gas, as a buffer gas in our atmosphere, or it's 80% of our atmosphere. So nitrogen serves a very important role, and we also know it as a fixing compound. So nitrogen has an important role in biology and on Earth. And so we would expect to find nitrogen-rich compounds on Mars as an indication that the table had been set for life early in Mars history. And that's what the rovers are finding.
Right. The next question is from Stefan. Why not also start crowdfunding for scientific research?
So a very good question, and it is happening. It's happening in various ways. I think the biggest reason why it's not happening more is that the research is so expensive. If we're talking about exploration of the solar system, the base sticker price on a moderately complex mission is about $1 billion, basically. I mean, the little Mars rovers, only one of which survives to this day, had a price tag close to $1 billion. These big missions like Cassini are multi-billion-dollar. James Webb is $8 billion. So those are pretty extreme. But even the more modest missions that are doing interesting things in the solar system, and certainly astronomy missions involving telescopes in space, they're just extremely expensive. They're beyond the role of crowdsourcing or funding mechanisms like Kickstarter. But for small-scale experiments, especially for prototyping things and testing out technologies, I think this crowdsourcing or crowdfunding is already happening. I've heard of examples of it happening. I'll give the most recent example I've become familiar with, because some of it's going on at this university involving student-led groups as well as faculty, involves CubeSats. So one of the exciting things about the miniaturization trend of technology is that you can now make very, very small satellites with quite sophisticated sensor packages, including cameras. As we know, cameras can now be miniaturized to the level that they could fly in a little robotic mosquito around the room and take pictures. So CubeSats are essentially, it's just an acronym for how you fit these small electronic package into a size that's something like 5 centimeters on a side, and actually can be a cube, doesn't have to be. And these CubeSats can then be launched en masse, where teams pool their resources to get a small fraction of the payload volume. They're quite light, of course, and everything is driven by weight when it comes to the cost of orbital launch. And so there are now dozens of university groups, including some that are purely run by undergraduate students, which is very exciting, that have launched CubeSats, that have put scientific experiments into Earth orbit. They've used commercial launch capabilities. They're not working with NASA or any of the big space agencies. They're just using the marketplace as it exists. And they're doing scientific experiments. Some of them are doing Earth-looking experiments, remote sensing. Some of them are trying to track space debris. And some of them are even attempting to look outwards and do astronomy, looking for transients or gamma ray bursts or flashes of light that are bright enough to see with a really small telescope or camera, because you can't really compete with the big telescopes on Earth. So this is one arena where crowdsourcing, crowdfunding has really played a role, and I know of some missions that have completely worked this way. I also know a couple of the Google Lunar Prize, the Lunar X Prize, if you like, which is an ongoing competition from which government agencies are excluded. It's for not for the deep pockets; it's for the small pockets of individuals, research consortia, and universities. That's the prize, $50 million on offer to any group that can land a rover, a small one presumably, on the moon, drive 500 meters, and send back data from a remote location. And I think of the 15 groups that are still in consideration for that Google Prize, 3 or 4 of them are using crowdsourcing or crowdfunding for their efforts, which cost typically a few million up to $10 million. So it's a great question because this has just started in the last few years. It's going to get bigger and bigger, and maybe it'll even work its way out towards some of the more ambitious missions.
All right, the next question is about the Hubble extreme deep field photographs. The question is, if we are able to see even further in the past, won't the density of galaxies at some point start to diminish? Would you please comment on the geometry of the universe, especially in regards to the distant past?
So I'll deal with the geometry question by WMAP, the Wilkinson Microwave Anisotropy Probe, the microwave experiment that lasted a decade that produced the most exquisite pictures of the microwave sky and cemented our information about the Big Bang. And that experiment, by looking at microwaves that had traveled across almost 13.8 billion years of space and time, was able to show that the speckles on the microwave sky had not been either magnified or demagnified in their passage across the universe, thereby indicating no demagnification or magnification from curved space-time globally, and therefore space being flat. So WMAP demonstrated that space is flat cosmically, our entire visible universe, to within about 1%, very, very close to completely flat. So that came from WMAP, not from Hubble. Hubble ultra deep field or extreme deep field has actually done what the questioner asked. It has indeed seen through the entire phase of the construction of galaxies and their turning on, and most of the stars in them forming and then starting to decline. We're in the middle of a long, slow decline of the star formation history of the universe, where the global star formation in any volume of space, accounting for space-time expansion, is now 10 or 50 times lower than it was at the peak about 8 billion years ago. So star formation grew rapidly in the first couple of billion years after the Big Bang, once galaxies started forming, and then it's had a slow decline as the universe thins out, less gas is available for forming new stars and new galaxies, and the galaxies fade. And so the Hubble extreme, or the ultra-deep field, is seen right through the peak of that star formation history, almost to the dawn of time when the very first galaxies were forming. The highest redshift confirmed for galaxies in the ultra-extreme deep field is 9 or 10. There's some arguments about the very highest redshift. That's a very competitive subfield of astronomy, but basically roughly a redshift of 10. That means the light has been stretched by 1 plus 10, a factor of 11, since it was emitted. It's an extreme amount of redshift. Also means the universe was 10 times smaller and 1,000 times denser then. So the ultra-deep field is looking back really early in the history of the universe, within the first 5% of the age of the universe after the Big Bang. And it has seen clear through the peak of the galaxy construction project and the peak of the star formation history, which is a fantastic success for a fairly modest-sized telescope in space. That's a success. The thing that it wanted to do that it isn't quite able to do, just not quite a big enough telescope and also working visibly and not in infrared, is look to the first light, to see when the very first light from galaxies emerged. And that's work that's going to be done by that James Webb Space Telescope.
Michael is interested in how we know about the expansion rate of the universe, and asks, is it possible that the universe has stopped expanding and is now contracting, but the blue shift light has not reached us yet? So could you just talk generally about the evidence for the expansion and acceleration?
Sure. So the expansion history of the universe, that's the general phrase I would attach to the question, and a major goal of cosmology to measure this, is a huge research agenda. It's taken hundreds of investigators decades to piece together the expansion history of the universe. And it's pretty well determined now. The first thing to say is the local expansion rate, that is the expansion rate right around us, where the look-back time or the distance to the nearest galaxies is tens or hundreds of millions of light years, which is a small fraction of the age of the universe. So you're still looking at local, recent time. That local expansion rate is very well measured, and that was a project of the Hubble Space Telescope. So the local expansion rate is measured with a precision of about 6 or 7%. It's a pretty well-determined number in cosmology, and that essentially says for every megaparsec, or 3 million light years you go away from the Milky Way, what is the recession speed of a galaxy going out by? And the Hubble constant, which is the word attached to that current expansion rate, is measured to be about 70 kilometers per second per megaparsec, which means for every megaparsec you go away from the Milky Way, 3 million light years roughly, a galaxy is moving away 70 kilometers per second. So if you go away 3 megaparsecs, or 10 million light years, the galaxies on average are moving away 200 kilometers per second, and so on. It's a linear expansion rate. And that is the global space-time expansion we see around us at the present day, because it's a local experiment. Now, when you go back further using these large telescopes and very clever methods like supernovae to measure the distance to these galaxies, which is the hard thing. The redshift is the easy thing to measure, the distance is the hard thing. And you have to compare those two in a Hubble diagram. Then you use the telescopes to look back in time. So as you look out in space, you look back in time, and you see how the expansion rate changed in the past relative to now. And what people anticipated, just to finish the answer here with one of the surprises of the last few decades, people anticipated in a Big Bang model that the universe should have been slowing down because the galaxies and all the mass in them, which is dark matter, should cause whatever the initial expansion rate was at the time of the Big Bang to slowly retard or slow down over time due to the gravity interactions attractive of all the galaxies on each other. That was anticipated, and if you reverse that logic, whatever the current expansion rate is, the expansion rate should have been different in the past. As you look back in time, you should have been looking to a time when the expansion rate was more rapid. In fact, what was seen was the opposite. Where the expansion rate now is faster than it was in the past, which indicates an accelerating universe. And that was the discovery in 1995 that led to the idea of dark energy. So now we piece together almost the whole expansion history of the universe. We have the present expansion rate, very well measured with Hubble Space Telescope, accurate to 6%. As we go back in time, we see that the universe decelerated, so it's been accelerating in the last 5 billion years. And then before that, we see what we originally expected, that the acceleration, the universe expanded faster at the beginning, slowed down, and then accelerated more recently. So all of these things have been seen in the expansion history. And it's pretty well mapped out over about 90% of the age of the universe now.
All right, the next question is from Kevin. I heard that detectors attempt to observe dark matter by looking for particles resulting from dark matter annihilating with itself. How did scientists come up with the assumption that dark matter particles will annihilate with others?
Yeah, it's a good question, and it actually only applies to one of the hypothesized forms of dark matter. So dark matter does not have electromagnetic interactions. That's basically the premise of dark matter, that it's a subatomic fundamental particle, as yet unobserved in the lab, which is why everyone's looking so hard for it. And it does not interact with electromagnetic radiation, so it doesn't emit or absorb photons. That would almost make it seem impossible to detect. But it does have a lot of energy, and so in principle, it can have a sort of self-interaction mode caused by its energy. The particle does have energy, even if it doesn't interact with radiation, creating annihilation radiation that can then be observed. Remember, any amount of pure energy can make particle-antiparticle pairs, and you can harness that out of a collision or just out of the energy of the dark matter particle itself. So people are using that as a sort of indirect way of looking at the But not all flavors of dark matter particle will do that. The most pure and simple way of detecting the dark matter particle that makes no assumptions like that is the one that just uses the mechanical properties of the particle. And so most of the dark matter detection experiments involve solid state detectors like germanium and silicon cubes with very large volume detectors that are extremely pure. Well, actually what you're looking for are photons, or the sort of resonant interaction, the mechanical interaction, if you like, of the dark matter particle moving through this lattice, a solid state lattice, and depositing energy in the lattice, which then can be observed with a detector. That's really how most dark matter experiments work. But because dark matter does have this potential to create annihilation radiation, people are looking for that signature in other galaxies. And there was a story, I think I commented on it in one of the discussion threads or in a previous Q&A session, where dwarf galaxies was found, one nearby dwarf galaxy was found to have annihilation radiation, gamma rays, which you shouldn't have because we're not supposed to be anything energetic at the center of a dark galaxy, a dwarf galaxy, but there is a lot of dark matter. So that was an imputation of dark matter in a dwarf galaxy.
Okay, the next question is about black holes. I read the gravity of black holes, of a black hole is such that close to the event horizon, time moves to a virtual standstill. From our frame of reference, material does not disappear into the black hole, but ends up in sort of a layer around the black hole, always getting a bit closer, but never actually moving in. If this is the case, how can a black hole, once it has formed, grow?
Yeah, it's a great question because it gets to one of the sort of paradoxical aspects of black holes, which relates to the different frames of reference. The frame of reference inside a black hole should, if it exists, if you can get there and do any measurement, is truly independent of the frame of reference of a distant observer. And that's part of the fact that a black hole is a separate piece of space-time, sealed off from the rest of the observable universe. So when we apply general relativity in the region around a black hole, moving towards higher and higher gravitational potentials and larger curvatures of space-time, then the prediction of general relativity up to the event horizon is as you described, or as the earlier question alluded to, that since nothing can escape, the redshift, the gravitational redshift of photons stretches to infinity. And the stretching of time to infinite dilation is just another version of the same thing, coming from the same equations. And so it is indeed a prediction of general relativity that, as seen from a distant vantage point far from that intense gravity, a physical object, should you observe a physical object, or radiation, should you observe radiation, will appear to be asymptotically redshifted to infinity, or time, if there was a clock on a spacecraft falling in that you could observe, that clock would appear to slow down asymptotically to freeze at the event horizon, taking an infinite amount of time to reach the event horizon. That's straight out of general relativity, where the event horizon essentially is the asymptote of these stretchings of time and space and the dilation of energy, the dilation of time rather, and the redshifting of energy. Now, from the vantage point of the black hole itself, something will fall into the black hole, and the person observing, the person in that situation, the photon falling in, the spacecraft falling in, will just observe their own reference frame, and they will observe nothing going on at all with time. They will, if it's a physical object, suffer extreme distortions due to tidal forces, but if it's a photon then, or particle, single subatomic particle, then it just falls in. So the black hole is able to grow, and there's no contradiction there. It's just that you cannot, in the same breath, compare the frame of reference of an object that is approaching and then falling into the event horizon with one that observes that passage from a distant vantage point where the gravity is weak.
Right. Jose asks, as chemical elements are well spread along the universe, and microbes could exist on the most extreme surroundings, would it not be logical to have found something on Mars or the Moon, as they are also several billion years old?
It seems that the ingredients for life will be dispersed through the solar system as it formed, yes. So in that sense, in terms of the question, yes. If the chemical ingredients for life existed at the position of what would one day become the Earth and the planets formed, then they probably existed at the position of the Moon having formed from a collision with the Earth early on, and Mars, and maybe other planets, interior planets too. So the chemical ingredients indeed exist, and the question about nitrogen on Mars, and there's carbon-rich material under the surface, is part of that discussion too. But the requirement for life, the requirement for biology is a little bit more exacting, because as we understand it, the minimum life unit, and we don't really know what the minimum life unit is, what's the minimum amount of genetic material required to make the very most rudimentary form of life. Nobody actually knows. But it is going to be something like hundreds of thousands of atoms in a sort of RNA strand that's able to template, hold information, and evolve with time. So that's a high degree of complexity, and that kind of complexity can only form, we think, in a liquid medium, so you need liquid water, and it can probably only form when conditions are stable enough over a long term for it to progress through the stages of complexity. And that's where the universe is not all built the same. That's where the region where the Earth formed was special, because the Earth was able to hold bodies of liquid water long-term and stable for this process to take place. Now that doesn't rule it out happening on Mars, because we now know that Mars had oceans that were stable, or shallow bodies of water over a significant part of its surface, and they were stable for a long period of time. It's just that they hadn't been there for a while. So those same conditions that led to life on Earth almost certainly existed on Mars, not the Moon, however, 3 to 4 billion years ago. And so it's completely plausible that a parallel evolutionary path produced microbial life on Mars. But since then, Mars has desiccated. It has become geologically inactive. Its atmosphere has disappeared. It's been pounded by debris and sterilized by cosmic rays and radiation. And so the evidence of that exciting early phase of potential biology is really hidden from us.
Right, the next question is, in most of the videos or animations I watch about stars and galaxies, not just in this course, the stars and galaxies seem to always spin counterclockwise due to angular momentum after gravitational collapse. This seems to happen in about 90% of cases. Is that for animation purposes, or is this the case that most stellar objects have that direction when spinning?
It's a good question, and that's very well noticed if you've observed that, because I've never kept track. I'm sure you're right, and I'm sure it's just a little subtle bias in how people represent rotation naturally. It may be even related, this is a question, and maybe I'll explore it, to the bias that we have in our culture over in-handedness in terms of left hand versus right hand. So we have a clockwise, anti-clockwise prejudice in our culture. It stems from sun worship and the way clocks move in our culture, and a preference for things that move from left to right as viewed from a certain perspective, and I think that's what you're talking about. So it's a great question, because to me it implies that this sort of cultural bias that's associated with handedness, that's actually been present in our culture for several thousand years, may have mapped all the way into animations in the modern era of stars and how they rotate. So that would be very amusing. That's almost a publishable result. It would be very interesting. But to answer the general question, no, there is no preference of the vector of angular momentum in the universe. Stars, in general, certainly in the solar neighborhood, are measured to rotate, and the rotation axes and angular momentum vectors are randomly oriented. Now, the Milky Way as a whole, of course, does have an angular momentum vector. And there's systematic rotation in the spiral arms and in the disk. So there's an overall order of the Milky Way galaxy. But again, the Milky Way galaxy is rotating and has an angular momentum vector. And the galaxies elsewhere, spiral galaxies that have angular momentum vectors, those vectors are randomly oriented as far as we can tell. So the universe as a whole, whether it's on the scale of stars to stars or galaxies to galaxies, does not show any preferential orientation in terms of angular momentum. Good question.
All right. Thank you for the course. My question is, what is your advice for aspiring undergraduates having a passion in astronomy for graduate studies, but currently being in a different discipline, say mechanical engineering?
That's a good question, and it's a tough thing to advise these days because universities are unfortunately siloed, which is to say that the disciplines don't connect to each other as well as they might, and it's hard for undergraduates to take a broad curriculum, even within technical subjects, that lets them move from one major to another. So, that's just an unfortunate part of the university system. I don't even think it's unique here. I have friends in Britain that complain about the same thing, and in Europe it seems the same thing. Most professional astronomers had a first degree that was physics, or physics and mathematics, or physics and astronomy, and occasionally astronomy. It's not a common degree, but there are astronomy undergraduate degrees. So that is the typical path. The particular path is through physics and mathematics, and that's the easiest path to go from undergraduate to graduate work in astronomy. But I have seen students, including one or maybe two with your major, go into astronomy. Now they're going to have to make up absences or deficiencies in physics by taking physics courses at advanced undergraduate levels, or maybe even a graduate level alongside their astronomy courses. But I would say a good student in that kind of a technical subject or closely related subject, if they find the right program that's willing to work with them, and of course if they are talented enough that the test scores and academics that they are competitive in just general terms, and GREs and so on, then it's not out of the bounds that you could get into a graduate program in astronomy. And in fact, even students coming from a physics background, some of them have been in programs where they've had one or maybe two astronomy courses, and so their astronomy is actually kind of sparse, and so the graduate program has to give them a lot of background astronomy information. The physics is good, but they don't have it applied in the universe in terms of astrophysics or basic astronomy. So there's a lot of cross-training that has to happen because astronomy is a particular discipline. But physics and math are at the core of what astronomers do. Astrobiology, the incorporation of biology into the curriculum, that's a fairly new and recent thing. And some students hybridize in that way. But coming to astronomy grad school from a biology degree, for instance, that question comes up in my department occasionally. That's a hard thing to do because the training is really quite different. The physics and math you get as a physics major really only overlap a modest amount of the biology and chemistry that a typical biology student gets.
Okay, the next question is, how do telescopes distinguish various photons they receive simultaneously, since quantum mechanically photons are indistinguishable?
That's a good question, and for the most part they don't. So in most detectors, so the telescopes themselves don't distinguish, they just scatter the light, they just receive photons and focus them on a focal plane in the detector. And the detectors themselves don't distinguish either. The typical detector in most optical telescopes, and even in some infrared telescopes, is CCD. It's a charge-coupled device where the photons are essentially reacting through a front surface to a layer of silicon, and they're creating electrons in a potential well, and the accumulation of light essentially corresponds to the accumulation of electrons in a potential well, which are then read out electrically along the lines and then rows. And so it's light turning into electrons that are then clocked or read out. And the individual photons are not tagged, so it's just a collection. It's just a bucket that's collecting those photons, and then a number is read out. But there are some detectors that do something a little more interesting. There's a set of detectors that used to be called MAMA arrays, micro anode multi-channel arrays, I think is the acronym, and they're relatives. And they're a little more interesting because they actually detect individual photons and they time tag them. So the photon arrives and it interacts with a charged wire, typically a micro wire, and that interaction is registered in time and space. And so that individual photon is recorded as it arrives at the detector. And these detectors are gathering they're designed for low light level where you're not inundated with photons. And so they can register the arrival of a photon to nanosecond, to micron levels in space, and to nanosecond intervals in time, which is sufficient to time and space tag all the photons arriving at the detector. So for some specialized purposes, individual photons are counted and time tagged, but for most purposes, 95% of all astronomy is done with CCDs that just put the photons in a bucket and don't distinguish between them.
All right. The next question is about the cosmological constant, and I think this will have to be our last question for today. Basically, Giselle would like you to help her explain the cosmological constant in layman's terms to some friends. So what is the cosmological constant and what's its relationship to the expansion rate of the universe?
Okay, that's a good question to finish about because it alludes to the biggest component of the universe, dark energy, which is 2/3 to 3/4 of the universe, and the thing that we don't understand very well at all. So it's the biggest mystery in astrophysics. So it's a good place to end. The best way to start by describing the cosmological constant is the historical way, which is how it got that name, cosmological constant. Einstein, when he developed the theory of general relativity, and others like Friedman who solved his equations, realized that these equations were dynamic. Basically, when general relativity was applied to a situation like a universe, it didn't tend to a static solution. The solutions were dynamic. In other words, the space-times were either growing or shrinking in the equations. That's just how the equations work when you solve them. And when Einstein visited Mount Wilson Observatory, famously in the early 1920s, after he published the theory, 5 years after he published the theory, he sort of asked what the state of the universe was. And since that was before galaxies were known, and the Milky Way was the only universe we knew of, and the stars were milling around, maybe they were rotating in the disk, but there was no net expansion or contraction, the astronomers essentially told Einstein the universe is static. It's neither growing nor shrinking. And so Einstein and others working with these equations realized that was a problem, because the astronomers have said the universe is static or stationary, or neither growing nor shrinking, and yet the equations really only produce solutions that are expanding or contracting. And so to make the solution of his equations match what the astronomers said the universe was doing, Einstein added a term called the cosmological constant. And it took the form of the Greek symbol lambda, the capital letter lambda in the Greek alphabet. And that's how astronomers still know dark energy. That's how they term it in their equations. And so basically, Einstein messed with his equations to put a term in it that would suppress the expansion or contraction, essentially working in opposition to the expansion or contraction to produce a static outcome. And so that was the cosmological constant. Now, 10 years later, the universe was expanding, and Hubble made his observations, and Einstein kicked himself. He basically said, I missed making a prediction. He missed trusting his equations and saying, the universe, I predict the universe, since it was unlikely it would be contracting, because then how logically wouldn't we be at the end point of that, where there was in the universe? Of the two possibilities, the most logical one was the universe was expanding, and he should have had the courage of his convictions and his equations by predicting the cosmic expansion before Hubble actually measured it. He considered that a huge missed opportunity. And so the cosmological constant that he conjured up to match what the astronomers told him the universe was doing, which turned out not to be accurate, became a relic of history. And then it came back into the picture in the 1990s, when astronomers found that the universe, instead of just expanding at an ever-decreasing rate, as standard Big Bang would predict, it was expanding at an ever-accelerating rate. And that was the discovery of dark energy. And it turns out that in the equations, the thing that would make the universe move at an ever-accelerating rate is something that works opposite to gravity. So if you have a universe that's naturally, say, shrinking and you want to make it static, you add in a cosmological constant. If you have a universe that should be slowing down and you find out it's accelerating, you add a gravitational constant. So the same mathematical term served in the 1990s to accommodate dark energy, what we know of as dark energy. And so it's a strange historical linkage, but the cosmological constant then became, in the 1990s, attached to this entity, this mysterious substance of the vacuum of space that causes the universe or space-time to expand at an ever-accelerating rate. So the cosmological constant has, is identified with dark energy for these reasons. That makes an assumption, though. To call it the cosmological constant makes an assumption that the entity we call dark energy has not changed over cosmic time since the Big Bang. That's a big question that we have not yet to answer with observations. It's not yet clear if dark energy is truly like a cosmological constant that's invariant in time and space, or if it may vary between one part of the universe and another, or if it may have varied in strength over cosmic time. People are doing those observations to test that idea, but they don't have the answer. But for now, the dark energy does seem to behave like the cosmological constant that Einstein dreamed up 100 years ago. So that's it for today, and thanks very much for all your great questions, as usual, today on everything from solar system to cosmology. And we'll be picking this up in a few weeks for our Udemy students, and then Coursera will continue through the summer too, so I'll be still doing live sessions for the rest of the year. Okay, goodbye to everyone.